So this is using F# to change the way we work. So this is a case study about a piece of work that my company did for one of the world's largest insurance companies at the beginning of this year. It went down very well indeed. So I'm going to split up my talk into three separate sections. The first one's talking about the ordinary delivery process, which I think you guys will probably recognise. It seems to be fairly ubiquitous in medium to large companies. Then I'm going to spend the middle of the talk talking about streamlining the delivery process. So what can we do to improve this? And then finally, at the end, I'm going to spend the last third actually talking about technical aspects of this stuff. So there's no real code in the first two thirds. It's all sort of businessy stuff, so don't worry about that. So we need to sort of bear in mind how we got to where we are to start with. So the way the computers are set up at the moment, the way that we use them, we're automating things that used to be done by hand, of course, before computers were brought in. And it's very important to bear that in mind. So the techniques that we're using at the moment did offer huge benefits over what went before. And these were order of magnitude benefits in terms of latency and throughput. So this is your performance, you know. So if you think about the latency and the throughput of an actuary working out an insurance quote by hand using a pencil, obviously the latency is a lot better now that you've got a computer doing it, right? But as Don touched on earlier, the fact that you can use more sophisticated algorithms when you're computing these kinds of things, when you've got a machine to crunch the numbers for you, that's a huge competitive advantage, and that's a big driver in this industry, in the whole finance sector. So I'm talking about this from an insurance angle, but I think this equally applies to the sort of trading side of things. So let's have a think about how a business delivery process works. So it starts off with my guy with a light bulb here, symbolising his idea. This is a business person. He's come up with an idea. It's something he'd like to change about the way the production systems are running. It's about what they do, the algorithms in them, let's say. So he or somebody near him, maybe a technician, is going to model the idea, and about 9 times out of 10 it probably turns out, if they're anything like me, the idea is a terrible one and they bin it, but that 1 time out of 10 they want to actually ship the idea. They want to turn that into a production solution. So they take a prototype that they've built in Excel, and they've got a sort of wordy description of it that they've come up in Microsoft Word, saying that these are my thoughts and feelings with regard to the algorithm. And they give that to somebody who's normally, traditionally, a C++ or a Java developer or something like that, who then takes that prototype and tries to turn it into production quality code, and in particular has to integrate that into a million-line existing legacy code base, which has to interrupt with a variety of sort of quirky, weird, exotic, I think that's the polite way of describing it, sort of legacy systems that sit around the outside using ancient databases, all this kind of stuff. And then only after that's been done do we actually get to sort of sit down and properly test this thing. So we're testing this thing often with tests that are derived from the guy right back at the beginning. Right? So this is a very long loop back up to the top if it doesn't pass the test. And inevitably, there's a lot of complexity in there, a lot of incidental complexity, and it fails some tests, right? So you end up going back up to the top. You have to revise often the model, then you give the new model back and you recode the solution. Perhaps it's because of some interaction between the production systems that the modeler wasn't aware of, because it's literally not his job to know about those production systems, right? So you keep doing that until it's fixed, and then ultimately you can deploy your production code, right? So we have to sit down and have a think about where there's room for improvements in here. So it's those iterations that are the really big killer. So the iterations themselves, in some sense, in an abstract sense, they're inevitable, right? So you have to keep testing your thing until you're confident that it's right. We'll have a look at how we could improve the iterations to make them go faster in a minute. So delivery speed and cost. So obviously this is a very long journey from the light bulb to the actual deployment of production quality code that's being tested. This takes often months, and it's typical for it to cost millions of pounds. The minimum I've seen in big companies is about 9 months, and £1 million is fairly typical for even relatively small changes. And the consequence there, there are knock-on effects. So if you come up with an idea that's an incremental improvement that's not that big, it'll never see it into production, because you can't justify those costs, you can't justify people working on it for that length of time, so it doesn't get done. So people back up the pipeline, they fill it with the biggest possible projects that they can, they get together all of the ideas and they shove it down the pipeline in one go to try and get it done. And that's because we've got this huge latency going from start to finish down this development pipeline. So I'm hoping you guys are going to be familiar with this one. I'll just go quickly through it. So first off, let's say you've had a slight discrepancy. The deadlines are 1 million miles away. Everybody's happy, everybody's feeling relaxed, and you have a civilized discussion. You sit down and you discuss these things. You've got these two people, one responsible for the modeling side, one responsible for the production code side of things, And then the second time around, things are getting a bit more tense, the deadlines are looming, they're in your back mirror, you can see what's going on, it's not looking so good, and then finally it just descends into this wild fighting, and the deadlines have slid, and you're way over budget, and everybody, this guy's getting kicked in the monads. It's just, it's just awful. Everybody's familiar with this, I take it. Looks like you are, I think. So, what objectively were the big problems that caused this? And I should say, by the end of it, actually, where that guy's getting kicked on the ground, that's when people stop organising just a meeting, right? And what they organise is, they stop calling it a meeting, they call it a workshop, right? You book out you get everybody in a whole day, probably in another city, if you're distributed across the world, get them all together there for a whole day, because obviously that's going to help, right? And so, what are the problems here? So we've got a bunch of problems with this, right? One problem is the accuracy. So, off the bat, we've got the guy doing the modelling. I mean, Microsoft Word is just the worst possible way to represent ideas, really. I mean, we're all about static time checking and machine verification and all this kind of stuff. Microsoft Word is obviously totally freeform. You can put any garbage you can think of into Word, and you can hand it off to the other guy. And of course, I'm not saying it's people do it deliberately, but there's every temptation to do that, because then you just pass off, passing the buck, you pass the problem on to somebody else. And this causes a huge problem, because this is the source of those iterations, right? So Excel is better, because at least you can run a prototype there. At least the coder who's actually doing the translation of this into the legacy code base, he's got a good, he can play with the Excel spreadsheet, he can get different answers out of it, he can work out what's going on. He's got a well-defined semantics, so it is executable, which is far more than can be said for Word. But at the same time, it's totally free form, right? So there's a lot of scope for him to put errors into there. So for example, in the production system, it's entirely reasonable that there are a certain set of possible inputs that could go into the system from some external system. So let's say there are 4 of them, right? And in the Excel, he may have put 4 in, but one of them might be a different one. He might have misunderstood what it is the production system does. And obviously Excel isn't going to know that, and the modeler's, it's not really his job to understand the intricate details of those neighbouring production systems, so he's not going to pick up on this. And it goes right the way through the pipeline until it gets to testing, and then people realise that there's this discrepancy. So the next one is the complexity. So the models themselves, I'm seeing quite a lot. In this particular case, the company had reached out for an off-the-shelf business rules engine, and I spent a long time with them, talking to them, having these whole day workshops. And I kept saying, what is a business rules engine? And they didn't know, but they really wanted one. They really felt they had to have this thing. And I think what I sort of reverse engineered out of it is, they reached for a business rules engine because what they were doing was a lot of dispatch. So by dispatch, I mean they're doing the kinds of things where in a traditional language, you would go for a massive block of nested if then else, if then else, if then else. Right? So you're testing a lot of predicates and you're dispatching various different ways. You can imagine drawing it as a flow chart or something. And that really looks horrific in Excel. There's no easy way to do that. Excel looks fantastic if you've got grids of cells, you've got auto-fill down, all this kind of stuff, recurrence relations, brilliant, eats that for breakfast. But dispatch is not so good at it. Doesn't represent it very nicely, doesn't execute it very nicely. Could look a lot prettier, So that's one of the big problems. Latency. So I've stolen a word from Rich Hickey here, who's resurrected this archaic word complected, which means to entwine or braid or interweave things. And I'm using it negatively here. So we've got 2 different kinds of testing, really. We've got the testing of the model to see if the model is actually right. Now, the modeler can test it to some degree, but he's not very good at testing whether or not it integrates correctly with the production systems, as I've said. Right? But on the other hand, you've got the actual sort of manual hand compilation of that Excel code into C++ or Java. You have to test that. You normally use something like unit testing for that. Right? So there are 2 different kinds of testing going on here, but we've complected them. We're doing them all in one go. And if there was an error in either, we go all the way back up to the top and start from scratch. So there's room for opportunity there. So I whopped out graphics and I typed in this sort of stuff in here. So on the right-hand side, you've got the stick man doing the flowchart. In the middle there now, you've got the exact same thing but drawn out in a more formal way. But in particular, I've coloured the vertices of the graph. So the green vertices are people on the modelling side. This is the actuarial side in insurance, but it's equivalent to many other industries. And the people on the red side are the production sort of application developers, IT, those kinds of people. Right? And the killer problem here is the fact that the back loop from tests to model goes between red and green. Right? So I'm deliberately taking social problems and phrasing them technically because I know you guys will tend. So That's the killer problem, right? So what can we do about this? So the first thing I did, I was trying to find stiff men. So I went to clip art on PowerPoint, I typed in man, and it came up with this image, which is described as man dropping dead fish down toilet while dog does not watch. And I thought, I've got to use that. I don't know why, I just like put it here. It looks good, I like it. That fish has an eye, so it really is a fish. So, a lot of people I see, this is answering your question actually, you asked earlier, so where does this kind of stuff go wrong? So the biggest problem I see is people take F# and they treat it as a panacea. They try to apply it everywhere, they don't consider whether it's applicable, they don't consider return on investment for using it, and they just sort of go. As soon as they get it, go. And so I think Don's answer was pretty much on the money when he said education and training and things like that, right? So we need to make sure that people know where F# is of the biggest benefit. So they don't go gung-ho, they don't just run in there and try and apply F# everywhere, right? So a lot of people come from potentially huge code bases and they try to just sit down and rewrite the entire thing verbatim from scratch in F#. I'm not saying you won't get some incremental benefits from doing that, but what I'm saying is that if you can see the forest for the trees, and you can work out how to change the entire end-to-end delivery process, instead of rewriting your existing solution and coming up with a near identical solution, if you can change the process itself, that can be a lot more productive. And the reason why I found F# is very good for that is that it lets me solve problems. I can solve problems with F# that I couldn't solve before, using any of the other tools that I've had before. And the reason is it's simply making the intractable tractable for a bunch of important things. Not everything, I'm not saying it's a panacea. So we can overhaul this delivery process. So let's think about a new delivery process. Anybody technical will realise that I'm now going towards DSLs, so domain-specific languages. That's what this is really all about. I've tried to avoid DSLs and TLAs in general because I consider it to be a rude word. So what we're really talking about is we're going to get the red guys, who are the technical guys. These are the software developers. These are the guys who use Emacs and know NUnit and all that kind of stuff. They can SSH tunnel. We're going to get them to build a tool, and they're going to give that to the green guys. Right? The green guys are the modelers, the actuaries. They have a high-level picture of things, but they don't want to know about the guts of the production system. And the green guys are going to use this tool not only for prototyping, not only for doing their modeling, testing their model, but they can deploy their model once they've tested it and they've signed off on it and said that we take responsibility for this thing. They can deploy it live into production themselves from their own desktop using this tool. They no longer give that to somebody to type in by hand in a language, C++, Java, F#, anything, right? So that's what this is all about. So why is this good? So we've separated the people and the jobs from each other, right? So we've got one person using the tool to turn ideas into products. That's essentially the business person, so on the business end of the spectrum. And the other person is responsible for maintaining the tool. So they have a clear job there as well. They're two completely separate jobs, right? And if you think about it in terms of one idea being put into production, provided that idea fits into the capabilities that the tool has, which is very likely, the red guys have no involvement whatsoever. But the green guys don't have to discuss anything. There are no meetings, let alone workshops. All that contention has disappeared from the system, right? And that's why this can be so much more productive. And also we've got separate tests. So the green guys are responsible for maintaining their tests. Now their tests can be written in any way that they like, in actuarial speak, using domain-specific, they can use typeset mathematics, they can use graphics, they can use whatever they want, they're not constrained, right? The red guys is just a challenge on the red guys to provide them with that. The red guys love that challenge because it's a lot nicer than maintaining a million line legacy code base, right? So they leap at the opportunity to do this, which is great. And the red guys then can maintain their own set of unit tests to test that tool, to make sure that tool is doing what it says on the box, right? So we've disentangled these two different forms of testing. We've got them completely separated. Now they're done completely independently by separate people who are experts in those kinds of tests, which is exactly what we want, right? So the big advantage is that the business people can now effectively ship products themselves. Yeah, which is obviously, that's a huge advantage, right? They're not waiting on these other people. And the business people, they don't like having these discussions with the technical people, and the technical people, they often don't like having discussions with the business people, right? And I've seen this over and over again in lots of different companies. So we've got a lot less contention in our system, which means iterations. So in other words, if the model is slightly wrong, the test showed it's slightly wrong, we have to tweak the model, change the test maybe, fix it. This guy, the red guy, the green guy, sorry, is doing it from his own desk in his own time, as quickly as he wants to do it, right? So that means these things take hours instead of months. So the benefit there is huge. Quicker time to market, so obviously the end-to-end process, because these iterations are a lot faster, the end-to-end time to market, and I'll go into a specific example later, is vastly quicker than it was before, the old system. Cheaper delivery, so all of those overheads, all of those times spent paying people to sit in meetings have disappeared. Happier employees, so the green guy's very happy because they can ship stuff more quickly. If there's any complexity that they can understand about their own model, they can see it immediately in the system. And the red guys have a lot more fun doing this because it's a lot more technically challenging for them. And also the delivery process is scalable. So we can add more tool users, so more actuaries or more quants or whoever's using the tool. And we can add more tool developers. We can just scale this up however we like because we've disentangled these two things. So it does work very well, however, it's not completely plain sailing. There are some substantial problems here, right? So off the bat, what I normally do when I meet people is I say, tell me what your dreams are regarding your work. If you had a tool that would just do everything, would just make your life lovely and fantastic, and what would that look like? You know, what are your dreams? But the problem with the domain-specific languages, you don't want to know what their dreams are. What you need to pin down in order to technically write the DSL is you need to get them to explain to you what language they dream in, which is actually very, very, very difficult. And I completely failed to do this. So actually I ended up following them around for 3 months and just listening to what it is they did, right? I listened to all of their ideas. I got all of the information I could about all the ideas they'd come up with in the past. And I worked out, if there was a language, it had to be a small enough language that we could implement. It had to be simple enough that the production guys were happy to put this, this full-on language into the production system. But at the same time, it had to be big enough to express all of the ideas that they'd come up with. And it turns out that one of those workshops actually paid dividends there. So they'd come up with, one of the actuaries had come up with an enormous set of worked examples. And he said, look, if we had a system that could do something like this, and here's a worked example, you feed in the numbers and you calculate it, it's exactly how it is, the numbers that it comes out with, all this kind of thing. We've gone over and over again, lots of different examples. So I took a week, it was not a 9 to 5 week, but in a week I managed to write a demo of a system that was completely programmable, completely configurable, totally graphical interface, so no like plain text monotype, green text on a black background, that kind of stuff. It looked a lot more like Excel than it looked like, Sharp, to be honest. And I put in as integrated tests, I had a little integrated test tab, I put in every single worked example that they had done on their workshop, and I made sure that my system replicated the answers that they had come up with exactly, to sort of 15 decimal places. And I showed them this on a computer, and I put it on their computers, and I said, play with it and see what you think. And they went absolutely bananas for it, and they said, we need this. How did you manage to write that in a week? That's amazing. So you can write the production version in a week as well. That's fantastic. We'll see you next week. And then I sort of had to go, okay, no, just like, that was a demo, But I managed to work it out in the end, and we managed to get this whole thing deployed. It took actually 3 months to develop, which was actually very impressive, I think. I won't blow my own trumpet, but given that they'd spent 6 months trying to tune an off-the-shelf business rules engine and they failed, and then we managed to write a completely new one from scratch, from nothing, in 3 months using F#, which is exactly the kind of thing you can do using F#, right? This is why F# is fantastic. This is the kind of thing that you can do because it's a languages thing, and F# is derived from the ML family of languages, all that kind of stuff. So that was a challenge. Training people was a challenge because this is a new system, right? It's a new language, they have to learn a new language, but also it's a new deployment process. So they have to learn a new deployment process, and there are issues there. So you've got business protection people asking questions about, how is this different? Is that why you're uploading an XML configuration file that's full of code? All this kind of stuff. You have to work out all about the plumbing. So we have to make sure that our production system can talk to all of the relevant neighboring systems in production. We have to get a really good handle on what exactly it is that they're talking. So a lot of these systems, because they're old, they predate the internet at this company, which is actually quite common. So you don't have luxury of things like schemas. You have to reverse engineer this sort of information, which is great because again, F#'s got this built in. So we built a bespoke business rules engine. Business users had a fantastic user interface, right? That was a really key thing. And the big part of that is graphics. So something I'll go on to later is the fact that although there's been a lot of talk about about DSLs in general, I don't know why, but people very often neglect graphics. And I think actually graphical languages are really important. And I don't think it's any coincidence that the biggest uptake that we've seen, at least, of F-sharp developers, you say F-sharp users perhaps, is actually not software developers. It's the people who have to talk to software developers. They're the ones who are picking up F-sharp. So there's actually the actuaries who would never touch even C#, but they want to learn F#, right? So I was going back up to talk to more actuaries to train more people. They've already got 30 people at this company using F# now, but their biggest uptake is actually on the actuarial side and not the software developer side, which is a very interesting tale. So the system that we built, we built in static type checking. It knows about production systems. It inferred all of the schemas, all this kind of stuff, so that it catches as many errors as early in that long development cycle as you possibly can. I think that's critically important. Mirrors the production environment. We've got code reuse, so the sort of client-side version that sits on the actuary's desktop, that mirrors the production system. It doesn't actually have a direct interface to the production system, but it knows what the production systems look like, so it mimics that, so they can see that. And then when it goes into deployment, the exact same code base is used to actually talk to the real production systems. So we've got nice code reuse there. It's got integrated testing, and it's completely tuned to the needs of those people. So this is a Wordle. If everybody hasn't seen a Wordle before, I'll let you absorb this. So basically what it does, it takes a pile of words from paragraphs of text and it displays it graphically, and the bigger the word, the more common it was in the text that you gave it. So this is Martin Fowler's DSL patterns web page, right? So this guy's very famous for DSLs, domain-specific languages. And it's very interesting. Parsing, model expression object, literals, nothing about graphics. I don't think there was any mention of graphics in the entire thing. So DSLs can be fantastic, but I would strongly recommend looking at graphical DSLs because business people feel very at home when they have a graphical application. And the key thing there is that they're programming, but they don't realize they're programming. That's what the graphics are there for, is to make them think that they're not really there. So, in my mind, and I'm not saying every DSL has to be graphical, but in my mind, I looked back and I thought, you know what, in 1995 I was working for British Petroleum using a domain-specific language. It had text-based graphics that looked like this, right? It was shipped in 1988. CFAX was 1974. And most domain-specific languages today look worse than this. And if you think about that, that's really embarrassing for software developers, right? We've come so far in so many respects. And a big thing for me is Windows Presentation Foundation is so easy to use from F#. It's so easy to write a graphical application. Why wouldn't you do it? You can start off with 10 lines of code and just grow it from there, right? And this is exactly the thing that F#, this is one of the major benefits of F# for me, was that there's no way I could have done those graphics. If you look at any of the, Camel and the Haskell and those kinds of languages, they're great for doing domain-specific languages, but text-only ones, right? Their GUI bindings are just atrocious compared to F#. F# has seamless interop with the whole of .NET, including all of the graphics. It's dead easy to do that kind of stuff, right? So we did this demo, as I said. It's slick-looking, easy to use, bespoke language, integrated testing. We got their own examples in it, and we ran it on their machines, so they loved all of that. For the final solution, we took 3 months to design it, which basically involved me following them around, and they didn't really understand why I was following them around, so that was quite awkward. But then, after 3 months, I managed to come up with a design. I did the demo, and I managed to build it in 3 months. The final code-based size, and this is very interesting as well. So this is a bespoke business rules engine. It's got client side, it's got 2 server sides, it's got 2 different languages, 2 interpreters, and a compiler in it. There's a whole lot of moving parts in there. It's not over-engineered, right? Those things were all there because we had to work around issues within the company. So they all have a purpose. The entire code base is written in 100% F#, and it's 10,000 lines of code. And that is a big deal, right? Because if you have some guy come on board into a company where you've got a 1,000,000-line legacy code base, you cannot expect them to read it. You cannot expect them to sit down and read 1,000,000 lines of code. And therefore, you quickly reach the point where nobody in your institution is familiar with the entire code base. And as a consequence, you've got a massive activation barrier there that you just can't cross. Anybody who wants to make a change, there's no go-to guy anymore. And that's why development grinds to a halt when you hit that sort of 1,000,000-line of code region, right? But this is the other end of the spectrum. If somebody joins up, even if they're not very familiar with F#, and they say, I'm unwilling to read 10,000 lines of code, that's embarrassing because it's so small. right? It's the difference between giving them 1 book and giving them 100 books. It's a big, big deal. So, let me just skip ahead. There we go. So, performance. So, I don't want to disillusion anybody here. So, the performance of this system was not fantastic by any means. The reason is they didn't need fantastic performance. All they needed was performance that was sufficiently good that it didn't impact the overall performance of their entire system, right? Which was not good. It was nothing like high-frequency trading type stuff, despite the fact that it was written in C++, which is very interesting because everybody knows C++ is really fast. Right? So we were getting about 20,000 messages per second, which was ample, right? We were getting under 35 milliseconds door-to-door latency, so that's not breaking any records there, right? But it was perfectly adequate for this system. As an aside, I can't help myself, I'm going to go off and say, on a different 3-month project for a different client, in F#, so this is 100% F# code, we managed to attain 200,000 TPS, which is pretty good, but 95% of messages under 114 microseconds latency, which is really, that really amazed me, because I didn't think a garbage collected language, obviously one with a real-time garbage collector you'd expect to do quite well, but something with just running on a general purpose .NET framework, I did not expect to be able to get results like that from it. So you can actually get very, very good latency results and pretty good throughput results. So this particular system was optimized for latency and not throughput. I should mention that was not running on one machine, right? That was a distributed system that was fault tolerant, so it could withstand any single failure within the system. It's completely asynchronous message passing, and it was using InfiniBand, which is the communication fabric used in supercomputers. So the hardware itself was designed to be fast. And there was one little tiny bit of code that I had to write in a specially optimized F# way to be completely allocationless, so as to avoid hammering the garbage collector, basically. But that was it. It was totally doable, which was fantastic. So we did this system earlier this year. It's shipped. There are some interesting aspects to that. So the training was done completely on the fly. While I was building the system, I was teaching people how to maintain it and how to use it. All the people who worked on it had a 1-week course. So they trained with us 9 to 5, all day, every day, for 5 days in a row in 1 week. Right? We trained 30 people, and we're going to go back to do some more again before the end of the year. So 5 teams in this company were using F# when I left, and that just organically grew, and that was because really of 2 different things. So one of those things was the fact that our project one of those things was the fact that our project had caught everybody's attention within the company to the point where F# was escalated to the point it was discussed by the board of directors of a multinational billion-dollar corporation, non-technical corporation. This is not a technical corporation, this is an insurance company, right? So that alone was quite a surprising thing, but it really raised a lot of eyebrows right the way across the organisation. That was one aspect. The other aspect was the fact that these guys, who'd been slaving away on a million-line legacy code base, written in a variety of exotic ancient languages, were absolutely sick to their teeth of it and desperately wanted to do something newfangled. Right? So this project came along and literally everybody's hands went up and they all wanted to jump on board and have a bit of this, which was fantastic. The enthusiasm is very, very important, actually. I found, having trained a lot of people, enthusiasm is more important than academic qualifications. Right? If people actually want to do this stuff, they can pick it up. And to be honest, F# is a very simple language. It's vastly simpler than C++. A lot of people can pick it up and do serious work with it in a relatively short space of time. So we did have an emergency that came in while we were developing the project. They said, look, we've come up with this idea. We estimate it's going to take 9 months and it's going to cost £1 million for us to do this the old way. This is big money. This is going to save us big money, but it's not big enough that it's going to offset that cost, right? Is there any chance you could get that in? And actually, yes, it turns out that we showed them how to do it using the tool that we'd given them, and it took 24 hours. We turned it around, put it into production in 24 hours. So that's the kind of gain that you're talking about. And that, for the first time in years, I've seen a change comparable to the original moving from doing things by hand to using computers. It's an orders of magnitude gain in latency and throughput for the project, right? Which is a huge benefit. So the maintenance now, so we've left, we've pulled out, we made it very clear to them from the get-go that we weren't going to try and go for vendor lock-in or anything like that. We trained them up, and they're maintaining it themselves. They've had almost no issues at all. I get the odd email asking me a question, but actually they're generally very happy, and the people who are there are really enjoying developing this code base because it presents lots of interesting challenges, and they're just glad to not be working on the legacy code base instead. I should stress these guys, these are fantastic people. They're really, really great people to work with. I love working with them, but they are ordinary developers, right? These are not rock star developers by any means. There was one person, I think, who had a degree out of all of them, right? None of them had a degree in computer science, so these were completely ordinary people, right? And if they can do this easily, then I think a lot of people can do this, right? So here are some of their comments. These are comments from people on both sides of the fence, so the green people and the red people at this company. Pattern matching is quite neat, as is the partial application of functions. This is incredible, because this guy, before a week of training, had never heard of pattern matching and partial application of functions. Right? So that's pretty cool. We are rapidly coming to appreciate the benefits when it comes to refactoring code. So that's a big deal. It's very easy to go to a piece of F# code and refactor it to do something different, because it's functional, because you've got first-class functions. It's as simple as that. It makes a big difference. One of the actuaries said, our plans are getting bigger each week as we can see more and more flexibility. It is great. So again, that's absolutely fantastic best case scenario. And this is after I've left. So these people have no reason to even give me any feedback. I'm very happy that they're still coming to me and telling me these kinds of things. So we're going from ideas to production code about 100 times faster than we were before. Our delivery costs, obviously a 9-month project involving dozens of people, cost a fortune. One guy on his desk typing stuff in and then shipping it, I mean, it's many orders of magnitude difference. It's a huge difference between the two. So, technical aspects of the solution. So this one is quite interesting. So, F# is good for programmatic user interfaces, graphical user interfaces. A lot of people shun F# for user interfaces because there's no natural MVVM, and there's, you don't throw XAML in there, and there's no MVVM or XAML in my solution either. I just wrote it as good old-fashioned code. Some of it was written as sort of 1980s code to try and squeeze as much performance out of the system as possible. But it works beautifully. So we've got some technical aspects here that I'm not going to go into in too much detail unless people specifically ask me, but I'll just cover the anatomy of the business rule. So determine VIP status. So we've got a name for our rule, right? That's something programmers often miss. If you just gave this project to a programmer, they would want to put nice names on. And for all we know, the business people want to write on a scrap of paper and pencil, take a photo of it, upload that to the program, and have that as their description of their business rule. And there's no reason why we can't let them do that. If that's what they want to do, it's up to us to provide that. We should facilitate that for them. So what we're saying here is we've got some input variables. We're looking at gender and marital status. Basically what these two rules here, we've got two rules, the horizontal lines. If the gender is female and the marital status is married, then the VIP status is VIP. Otherwise, for any other values, in which case our DSL displays it as empty cells, we're going to set VIP status to normal. So these are our patterns on the left-hand side. We're saying, do those values, gender and marital status, match these patterns? And on the right-hand side, we've got the output variables. You could have as many as you want. Here I've only got one. This is called VIP status. And then we've got some expressions here. So these are text boxes that you can type expressions in, even mathematical expressions if you want to. That's up to them. So we took a leaf out of Excel and we said, look, in Excel, you type in Excel, you can type in an editable version where it displays the actual expression that you're typing in. But then when you press enter, it displays a display version, which is different. It no longer displays the equation, the expression that it's evaluating. It now displays the value that it evaluates to. Right? So we did the exact same thing here. If you've got the display version, so you've got the display version here. If you look at this cell up here, where it says married, married. If the person editing the rule clicks on that, it turns into this. Right. So this is very interesting, right? This is very interesting for a number of reasons. It's blindingly obvious what it's doing. Anybody can understand what it's doing, right? You've ticked a checkbox that says married. If I uncheck that and I check the one that said single, that will rule would fire when the person was single instead, right? But the fact that we're using these checkboxes to express this combination, that provides a kind of type checking, because it means the user cannot enter invalid inputs. For example, a marital status foo that doesn't exist, which is nonsensical. You can enter that into an Excel prototype, but you can't enter that into this. So here's some code I can go over. I'll just skip on to the last one. So we did have some challenges. So if anybody's interested, I can go either over the code that I've just put on those slides, or I can go into more detail on the challenges that have more slides. But that's the end of my talk. Thank you very much for listening to me. Any questions? Yes?
Can you please turn down the temperature?
Yes, I set that up.
And in hand.
Any other questions? Yes.
Is that the only GUI you had for your, was that your DSL, the GUI?
Yes, so this is what part of the user interface looks like. It would look like that. So when the person, it has a display version that gives you a nice clear depiction of what it is that it's trying to accomplish, and then when you click on an individual bit of it, that individual bit becomes editable and displays more information that you can change, so you can change what the rule does. The entire thing consists of a bunch of these stacked vertically. So the execution enters at the top, it tries to fire any of these rules starting from the top down. If they all fail, if one of them fires, then it drops down to the next block of rules. Does that make sense? Yep.
I was just hoping you had a more useful example, something that wasn't as trivial as that.
I'm afraid yes, so I can't go into the specifics of this particular solution, so I can't do that. But I can show you offline some of the other stuff that we've done that's very similar. Yeah. But you can see how this scales up. So you can add columns and rows, and you can add more input and output variables, and you have a schema that tells you exactly what you're allowed on the way in. And then you've got static checking that makes sure that you don't use things that you wouldn't have access to or that don't exist, and so on and so forth. Any other questions? Yes?
So you put all these non-technical users writing lots of code.
Yeah.
What's the long-term prognosis for maintenance, technical debt? Can they break your architecture?
So, potentially, yes. We don't know where this is going to go in the long run. Historically, what you would describe as the code that they have been writing has actually been very simple. And this is the big problem, is that these guys ultimately are the guys with money, and they don't understand why their simple ideas take so long and so much money to put into production. So this system has let them put those simple ideas into production. Now, the problem then is because they can now put simple ideas in production, undoubtedly they're going to make their ideas more complicated. But that's a bridge that we're just going to have to cross when we come to it, to be honest. Any other questions? No? Good. Thank you very much.